afternoon, wherever you are watching this. This is a shear force diagram of a simply supported beam, or an axle or bit of metal with a UDL, a uniformly distributed load. There's no point load, points. There's no point load, we've just got a UDL. That could be the weight of the beam, or it could be snow or something. It's just a uniformly distributed load across the entire length of this beam. There's no point load, just a UDL. So the UDL value, the uniformly distributed load value, is 1.5 kilonewtons per meter. So every meter we got 1.5 kilonewtons. So we've got to draw a shear force diagram, or sketch. Don't forget, draw is with a ruler and a bit of graph paper. Sketch is still with a ruler. So I'm probably going to sketch this, but it's better with the graph paper really because it's a bit more accurate. So we need to draw the shear force diagram for this beam above. First of all, we need to work out RA and RB, these reactions. We've done this a few times. So you need to make sure that we know how to do these reactions, because if you get these two wrong, then everything else will be incorrect. Now, before we start this, from previous examples, you should know that when you've got a UDL like this, which will convert into force in the middle, the RA and RB are going to be the same. They're going to be half of what the downward force is. But we'll work through it anyway, because that's the proper way to do it. So, calculate RA and RB. We've got to do them first before we do the shear force diagram. So don't forget, we've got to assume that, get a bit smaller one. Some of the forces equal 0. Some of the moments have got to equal 0. Clockwise moments are positive, anti-clockwise moments negative. The beam is in balance and moment is force times distance. Some of the forces just means whatever's coming up has got to be coming down. If you've got 11 newtons coming down, you've got to have 11 newtons coming up. Not saying that we've got 11 newtons down, but so it's got to balance out. The moments have also got to balance out, because we don't want this beam to be going up or down or tilting, twisting. So the beam is in balance, which means it's not going to move anywhere. So the first thing we've got to do is convert this UDL into a point load, like we've done before, because we can convert all of this UDL into a point load, which makes it a little bit easier for us. So the way we do that is, we know the UDL is 1.5 kilonewtons per meter, which means we've got 10 meters worth of it. So the equivalent point load of 10 meters of this 1.5 kilonewtons is going to be 1.5 times 10 to the 3, which is 1.5 times 10 to the 3, times by the length that the UDL acts over. In this case, it's acting over the entire length of the beam, which is 10. So to convert this UDL into a point load, we'll just multiply that 1.5 kilo by 10. You shouldn't need a calculator for that, but I'll just show you. Like 1.5 times 10 to the 3 equals that, times by big 15,000 newtons, or we plus ENG, 15 times 10 to the 3 newtons, which is 15 kilo. Now if you remember, this acts halfway along the beam, i.e. in this case the beam is 10 meters long, so this 15 is going to act 5 meters in halfway. So that's nice and easy. Now we can use this to work out our reactions. I'm going to have a cup of tea. So RA and RB we need to work out. Like I said before, when you've got a force smack bang in the middle like that, both of these forces I'm expecting to be 7.5. So we've got 15 coming down, which means we've got 15 coming up. So both of these are going to be 7.5. That only works when you've got a force in the middle. It doesn't always as easy as that. But we'll do it anyway just to prove it. So the point load is exactly in the middle of the beam, therefore RA and RB should be 7.5 kilonewtons each. But we'll check for a bit of practice, because practice makes perfect. So I'm going to find RB. I'm going to take moments about point A. Let's get another color. So that's going to be my pivot point here, point A there. And I'm going to find RB, which I'm expecting to be 7.5. So we know moment is force times distance. Here's my first force. It's the 15. So there's my force, 15. Because moment is force times distance. And how far away is this 15 from this point? 5 meters. So 15 times by 5. There's the pivot point. This force is trying to make this beam go that way, which is clockwise. So we'll leave it as a plus. And then we're going to add them all up because it's some of the moments. So you could put an add there, but it's easier just to put a minus because this RB, there's my R. We don't know what it is. We assume it's going to be 7.5. It's trying to push this beam. There's the pivot point. It's trying to make it turn anti-clockwise. That's why I've got a negative there. Force times distance. There's the force. We don't know what it is, but put it in. And how far away is this force from this point? It's all of that, which is 10 meters. It's going anti-clockwise, negative. All that, some of the moments have got to equal 0. Look, some of the moments have got to equal 0. Make sure you put 0 there. What I've done there is I've done 15 times by 5 is 75. This minus RB times 10, I've brought it across to there. So now we've got RB times 10, so we made it positive. Nice and easy. And then from that, then you should be able to leave the RB there. This is times by 10, so to get rid of that, divide both sides by 10. That's what you're doing really. That gets rid of that, and we leave the 75 over the 10 there, leaves the RB there. So therefore, that means therefore, reaction B is 75 divided by 10. 75 divided by 10, you should need a calculator. 7.5, don't forget it's killer. So you've got to put the K on the end. Don't forget, like kilonewtons, I've just used 15 rather than using 15,000, but you need to make sure you put the killer at the back end. So RB is 7.5, which we sort of guessed. So that's nice and easy. What you could do now is just take 15 take away 7.5 will give you the other 7.5 obviously, because we know that there's 15 coming down, which means RA plus RB has got to equal 15 as well. So that's one way you could do it. Obviously you need to check yourself, because if that 7.5 was wrong, then everything else would be wrong. So get into the habit of using moments both ways. So now to find RA, I need to take moments about point B. So I'll go back to my graph, get rid of some of this. So I'm now going to get rid of some of this, get rid of some of that. So rid of all of this. So now we know RB is 7.5. I'm now going to try and find, what color do you want? That one there. I'm now going to find RA. I'm going to make this my pivot point. I'm going to take moments about this point. So there's my 15 again. My 15 is going to be going anti-clockwise this time. And this RA is trying to be going clockwise this time. So the 15 is 5 meters away again from there to there. So force times distance is going to be 15 times by 5. It's going to be anti-clockwise this time. So there'll be a minus number in front of it. RA is going to be RA times by how far away this is, which is 10. So it's going to be RA times by 10. It's going to be a plus because it's going clockwise. So there's my 15 times by 5. 15 times by 5 is a negative number because it's going anti-clockwise. And then plus RA times by 10. There's my RA, trying to find it. It's 10 meters away from our pivot point, and it's going clockwise. That's why I've got a plus there. Don't forget, some of the moments have got to equal 0. That's why I put a 0 there. Make sure you do that. So what I've done there is I've done this minus 15 times by 5, which is 75 really. I've brought it across straight away to make it plus, to make it nice and easy. This negative term will plus it both sides, so it gets rid of that side there and leaves it here, makes it easy. So 15 times by 5 is 75, RA times by 10 is 75, just like before. Divide both sides by 10, just to get rid of that, that's what we're doing. So that 10 goes, 75 divided by 10, so RA is 75 divided by 10, which gives me 7.5 kilonewtons as expected. Don't forget the K. Don't forget the K. So we sort of knew that anyway, because we had 15 coming down in the middle, smack bang in the middle. So both are going to be 7.5. If that 15 wasn't in the middle, then these wouldn't be 7.5 and 7.5. They still add up to 15, but one would be bigger than the other. So now we know the moments. So 7.5 and 7.5. We can now draw the shear force diagram. So don't forget, with shear force diagrams, we're just looking at what we can see. So I'll get rid of some of this rubber. So all we're looking at is what we can see. Right? What we can see at certain distances. Now, take a note of this. When you're doing the shear force diagram, we'll use this 7.5 because these are forces. Don't use this. You need to use the UDL. So I'm just going to write in here 7.5 so I know. 7.5 there and 7.5 there. You need to include the UDL now. In previous examples, we just had point loads and no UDLs, but with a UDL, we need to include it. Include this number. So, first one, x equals 0. All we can see at x equals 0 is that 7.5 coming up, just like in a previous example. Get rid of this. So at x equals 0, which is here, all I can see is a 7.5 coming up. That's all I can see. There's no UDL yet because it's per meter, so I can't see anything. So my shear force at that point is going to be 7.5 kilonewtons. So I'm going to have 2 points really. I'm going to have 0. It's going to go up to 7.5. So that's the first point. So x equals 2. So I'm looking now, what can I see at x equals 2? Well, x equals 2 is about, well, there's 5. Look, so it's here, someone say. At x equals 2, right, forget all of this, ignore this. What can we see here? I can see the 7.5 coming up, and I can also see 2 meters, because now we're doing x equals 2. I can see 2 meters of this 1.5 kilo. So I've got 7.5 coming up, and I've got 2 meters worth of 1.5 coming down. So at x equals 2, I've got my 7.5 coming up. That doesn't change. But coming down, I've got 2 meters worth, because I'm x equals 2, 2 meters worth of my 1.5 kilonewtons. So 2 times by 1.5. Make sure you include that. So put that in your calculator. So I'll do 7.5, take away 2 times by 1.5 equals, should be the calculator, 4.5 kilonewtons at x equals 2. Now I'll go to x equals 4 and see what I can see. So at x equals 4, so now we're at 4, which is going to be, there's 5, so 4 is here somewhere. So I'm just looking now what I can see in here, ignore the rest of this. All I can see is my 7.5 coming up, because that's still there. And I can see 4 meters worth of my UDL, because I'm 4 meters in, so I've got 4 meters worth of my UDL. UDL is 1.5, and I got 4 meters of it. So at x equals 4, I've got 7.5, that's my force coming up, and I got 4 meters worth of my 1.5, because my UDL is 1.5. Don't forget the killer. So in your calculator, do 7.5, take away 4 times by 1.5. Close the bracket, press equals 1.5 kilonewtons. So at x equals 4, I've got a shear force of 1.5 kilonewtons. So nice and easy. 4 meters, 4 meters. Look, there's a trend, 2, 2, 4, 4. Now, I'm going to go to x equals 5 because at x equals 5, that is where the maximum bending moment is going to be, because that's what we're trying to find out, really. If I've got this force like this, which is the UDL force really, that beam, if you think about it, is going to be bending like that. And the maximum bending moment is going to be in the middle, which is going to be x equals 5. So I want to see what the shear force there is, because when there's maximum bending moment, there's 0 shear force. So I know that at x equals 5, I'm going to get the maximum bending. Normally, you'd have to trust the shear force diagram to find that. So if you went to x equals 6, you'd miss that point. So I'm going to go x equals 5 because I know that that is where I'm likely to see the biggest bending moment. So I'm going to go to x equals 5 because that is where it's going to be. X equals 5, which is here somewhere. All I can see at x equals 5 is this 7.5 here and 5 meters worth of this 1.5. So x equals 5. There's my 7.5 and I got 5 meters worth of this 1.5 because that is 1.5 kilo. 1.5, I've got 5 meters worth. That's the force coming up. 5 and 5, look. So where there's 0 shear force, there's maximum bending. So this looks correct now because at that point, halfway along the beam, I've got 0 shear force, and in the next couple of videos, we'll be doing this beam. We'll be doing the bending moment for this beam. So naught. So at that point, there's 0 shear force, but there's maximum bending. So, Vika. When we do the bending moment for the shear force, this example, we will find that the maximum bending moment is at 5 meters. So that's the reason why we do shear force diagrams first, is because the shear force diagram will tell us where the maximum bending moment or moments will be. Because when the shear force diagram crosses 0, that's where the maximum bending is. So I've done 5, naught, I go to x equals 6. So it's quite easy now, we'll just carry on. So at x equals 6, I'm just looking at what I can see at x equals 6. So 6 is here somewhere. Ignore the rest, ignore this. All I can see is that 6 meters worth of 1.5, and this 7.5 is still there. That's coming up. These are coming down. So it's going to be 1.5 times by 6, and the 7.5 is coming up. So 6, 7.5 coming up, and I've got 6 meters worth, 6 meters worth, 6 meters worth of this 1.5. 1.5. So you will see it's a bit symmetrical look because it's a uniform load. So 7.5 take away 6 times by 1.5 gives me minus that, like 1.5. Don't forget the killer. So at x equals 6, I got a minus shear force now. Don't forget you can get positive and negative shear. Different directions, because don't forget beams will bend in different directions. It's not a negative force, it's just a direction. So that's x equals 6. As you will see now, these are very symmetrical. They should come back to naught, which they will. So when you're doing these, hopefully come back to naught for you. At x equals 8, I'll just do it anyway, but you may have got it by now. So at x equals 8, we've got 8 meters worth now. So we go here, 8's about there somewhere. We've got 8 meters worth of this UDL at 1.5, so it's going to be 8 times by 1.5 coming down, and this 7.5 coming up. So 8 meters, I've got 7.5 coming up, and then I've got 8 meters of my UDL. The UDL is 1.5. UDL is 1.5. Cancel that. UDL is 1.5, and we've got 8 meters worth of it. Very symmetrical now, look. So I'll still do it. 7.5. Take away 8 times by 1.5. 1.5 gives me minus 4.5 kilonewtons. Nice and easy. And then x equals 10. I'm hoping it comes back to 0. Don't forget, because the beam is in balance, it's equilibrium. So we should get noughts and noughts at this end. So at x equals 10, I'm going to have now, how much of the UDL have I got? Well, I've got all of it. I've got all the UDL. So I've got all of this UDL. So I've got 7.5 coming up. I've got 10 meters worth of this 1.5. So there's going to be 10 times by 1.5, 7.5 coming up. And don't forget, I've also got this 7.5 here. So we're going to get 2 points at this point. We're going to get the 7.5 coming up and the 1.5 times by 10 coming down. That'll be 1 point. And then this 7.5 will be coming up to bring us back to 0. So hopefully we'll be minus 7.5 now at the bottom. That's the way of testing, like. So it's here, like 7.5. So we know we're correct because we've got minus 7.5, and then we've got the reaction 7.5 coming in to make us 0. One way of knowing you're correct, if you've got a minus number there that's equal to the reaction coming up, you're spot on. Don't worry if you're slightly out, because your rounding may be a bit out. So at x equals 10, I've got 7.5 coming up, and then I've got 10 meters worth of my UDL at, my mouse is going slowly, 10, so 1.5 times by 10, that's going to give me minus 7.5, and then I've then got this reaction RB kicking in, is coming up, look, bang, there, 7.5. So then we've got minus 7.5, because there's my minus 7.5. And we've got this plus 7.5 coming in. So that will bring us back to 0. Nice and easy. Bang. Now, the last bit, we've got to plot, draw the shear force diagram, draw, sketch. Draw means use a bit of graph paper. Sketch means use a bit of paper, but as long as you use a ruler and get your scale correct, you're laughing. So I'm going to plot now all these points. So 2, 4, 6, 8, 10. So that's going to be across the X, and then we need to go up to about 7.5 and then down to about minus 7.5. You will see with a UDL, it's a sloping line. So every time you've got a UDL, it'll be sloping. So don't forget, starts off at 0. So we've got 0 there. So we've got 0 there, starts off at 0. Then this 7.5 kicks in. 7.5 kicks in, 7.5. There, thank you very much. Up 7.5. And then x equals 2, we got 4.5. X equals 2, 4.5. Plot it. Make sure you get your scale correct. Label the units. Title, label. X equals 4, 1.5. X equals 4, 1.5. A UDL is a sloping line, so it should be sloping like this. If your numbers don't hit this line, there's something wrong somewhere. At x equals 5, now at x equals 5, we've done it because it's 0. So it is 0. So x equals 5. If you'd have gone to x equals 6, right, minus 1.5 at x equals 6, when you draw the line, it would have come through 0 anyways. So and then x equals 8, we know now it's symmetrical, minus 4.5, minus 4.5, and then 10 is minus 7.5, minus 10, look, 10 minus 7.5, and then this 7.5 kicks in, so you've got 2 points, plot that point, and then plot that point. So with the UDL, you'll have a sloping line. So if you look, it comes up. So this bit here really is our reaction A. That's our reaction A, coming up, up like that. The UDL kicks in, kicks in, kicks in, sloping line down, sloping line down. At the bottom, at the end, we've got RB. Come on, mouse work. We've got RB coming in 7.5. So with the UDL, we'll have a sloping line like this. So with a point load, because that force there is a point load, it's a straight line up or a straight line down, whatever. A UDL is a sloping line. This point here is very important because it's 0 shear force, which means when we do the bending moments, that will be where our maximum bending moment will be. Shear force diagram for a beam with a uniformly distributed load. Nice and easy. It's the same process as any other method for shear force diagrams. The next one we'll do will be with a shear force diagram with a load and a UDL. So I bet you can't wait for that. But for now, I'm going to finish my tea over and out.